Today on AI Paper Podcasts, we are breaking down LaViT, aligning latent visual thoughts from multimodal reasoning by Linquan Wu, Tianxiang Zhang, and their team.
Right, from City University of Hong Kong and others.
And we are just jumping straight in because this paper points to a really critical flaw in current multimodal large language models.
They call it the perception gap.
The perception gap. Basically, when you distill a big teacher model down to a smaller student, the student gets really good at learning what to say.
The textual mimicry.
Exactly. But it completely fails to learn where to look. It has no real visual grounding.
And LaViT is the proposed solution. It's a framework that forces the student model to auto-regressively generate these latent visual thoughts. It has to reconstruct the teacher's attention path before it's even allowed to generate text.
And they have this clever trick to make it work, curriculum sensory gating, which basically stops the model from cheating.
It prevents shortcut learning, yeah.
And the results are, honestly, they're pretty staggering. We have a compact 3 billion parameter model that's not just beating a 7B model like Qwen 2.5 EL.
It's actually rivaling, and in some cases beating, GPT-4.
Right, on really complex reasoning benchmarks like BLINK. We're talking up to a 16.9% gain in some visual grounding tasks. It's a huge efficiency unlock.
It really is. It challenges this whole idea that you just need more and more parameters. This suggests better attention engineering might be the way forward.
So let's really dig into that perception gap. The standard assumption in knowledge distillation has always been, if the student's text output matches the teacher's,
then it must have learned the reasoning. Success.
But this paper just says, nope, that's a dangerous assumption.
It really is. It's like the clever Hans effect, but for AI. The horse just looks like it's doing math.
So how do they prove this?
They introduce a metric. It's called the visual focusing score, or focus. And it's simple, really. It just measures how much of the model's attention is actually on the ground truth object versus, just staring at the background.
And when they applied this, they found something they call attention drift.
A huge drift. They looked at 1,000 samples from the visual coat dataset and found that even when the text was a perfect match, the student's gaze was... well, it was all over the place.
So it's saying the right thing, but looking at the wrong thing.
Or not looking at all. They did this great breakdown by token type.
Oh, this was fascinating.
Yeah. So for functional tokens, your stop words, like the, is, a, the attention gap between teacher and student is almost zero.
Which makes sense. You don't need to look at an image to predict the word is.
Exactly. But then you get to attribute tokens.
Adjectives, colors, spatial words.
And the whole thing falls apart. The gap just explodes. The student basically starts looking at the image and just relies on its language priors.
It's just guessing. If it sees the word fire truck in the prompt, it's going to guess red.
It's guessing red. It doesn't bother to check if maybe this one is yellow. They call it blind guessing.
And they can actually measure this, right?
They can. They found a direct link. When that SOCA score drops below 1%, the model's hallucination rate just spikes.
So it's not just a theory. It's a direct correlation.
It is. The model is just parroting the teacher, but it hasn't inherited the teacher's ability to actually see.
Which is why these smaller distilled models can feel so brittle. They're good guessers, not good perceivers.
Exactly.
Okay, so let's unpack the fix. LaViT, latent visual thoughts. How does this architecture actually force the model to look at the image?
The whole idea is to shift from thinking about an image, which is just captioning, to thinking with an image.
Using it as part of the process.
Right. So in a normal MLLM, the language model attends to the visual tokens and spits out text. LaViT sticks a step right in the middle.
And that's the latent tokens.
That's them. Before the model can generate any text, dollars, it first has to generate a sequence of these continuous latent tokens, which they call $.
So they're like containers for visual information. A bottleneck.
I'd call it a cognitive buffer. It has to compress all the important visual reasoning into these vectors first. And this is the key. The supervision for those tokens comes from something they call white box trajectory distillation.
All right, this gets into the loss functions. They mentioned 2 main targets.
2 targets, yeah. The first is semantic reconstruction, or ALES-Dexter. That's about aligning the student's latent thoughts with the teacher's high-level concepts, making sure they agree on what you're seeing.
To what? Okay.
But the second one, trajectory alignment, or less cross, that's the real magic. This loss function forces the student's attention map its gaze to directly mimic the teacher's gaze.
It's learning where to look.
It's explicitly learning where to look.
But hold on. We know these huge models can be messy. A 32 billion parameter model might glance at 10 different things before it finds the right one. Do you really want to teach the student that kind of scattered process?
That's a great question. And no, you don't. That's why they don't just copy the teacher's raw attention map. They're smarter than that.
What do?
They apply top case sparsification.
Ah, so they filter it.
Exactly. They only distill the top 8 strongest attention points from the teacher. They're basically telling the student, ignore all the teacher's hesitation and second guessing. Just focus on where it stared the longest.
So you're not just distilling knowledge, you're distilling focus.
You're distilling focus and filtering out the noise. It's a critical step. It stops the student from learning the teacher's bad habits.
Okay, so that's the architecture. Generate latent tokens to mimic the teacher's focus, then generate the text.
But the paper puts a huge emphasis on this curriculum sensory gating. Why is that so important?
Shortcut learning.
The model gets lazy.
The model is always going to find the easiest path to minimize loss. If you give it direct access to the image features and these new, complicated latent tokens,
it's going to ignore the hard part. Of course, it'll just look at the image directly and go right back to blind guessing from text priors because it's computationally cheaper. It bypasses the whole thought process you're trying to build.
So how do they stop that?
They force the issue. The training has 2 phases. Phase 1 is sensory warm-up.
I like that name.
And it's very literal. They basically blindfold the model's direct path to the image. They set this attention bias by a huge negative number.
So the text decoder can't see the image at all?
Not directly, no. The only way it can get visual information is by going through those latent tokens, $5. It has no choice but to learn how to use that bottleneck.
It's like you're forcing a student to actually take notes during a lecture.
And then taking the slides away.
Right. So they have to write their essay based only on the notes they took.
It's a perfect analogy. And then, once that habit is ingrained, they move to phase 2. They use a cosine schedule to gradually open the gate so the bias goes back to 0.
But by then, the model has already learned the note-taking skill.
Exactly. The core reasoning strategy is already internalized. The direct visual path then becomes what they call residual perception.
So we can go back and check the source material.
Right. It can look at the raw pixels for fine-grained details, reading tiny text, checking a texture, things that might have gotten lost in the compression of the latent tokens. But the main structure of its thought process is already set.
That's a really elegant solution.
It is, and the ablation studies prove it's necessary. Take away that curriculum gating, and performance on the MMVP benchmark just plummets to around 59%.
The model just never learns the discipline.
Never learns.
Okay, let's talk numbers, because we said at the top that this 3D model is going toe-to-toe with GPT-4o. That can sound like hype, but the benchmarks are very specific.
Very specific and very robust. They focused heavily on the BLINK benchmark, which is designed to punish models that just rely on text. It's all complex visual reasoning.
Like what?
Relative depth, spatial puzzles, IQ test style patterns, things you absolutely cannot guess.
And on relative depth, specifically?
LaViT 3B gets a score of 78.23%.
Okay, and GPT-4o?
64.52%.
Wow. That's almost a 14-point gap. A 3 billion parameter model is judging depth better than a state-of-the-art frontier model.
And it gets better. On the IQ test part of the benchmark, LaViT is at 32% versus GPT-4o at 30%. And maybe most importantly, it consistently outperforms its own teacher, the Quen 2.5 VL32B model.
This is the student surpasses the teacher thing. I mean, usually with distillation, you expect a trade-off. You get a smaller, faster model, but it's a little dumber.
Right. You accept some degradation.
But here, the student is actually seeing more clearly than the teacher. How is that even possible?
It goes back to that top case sparsification we talked about. And the entropy analysis they did is key.
Okay, break that down.
They measured the entropy of the attention maps. The big teacher model has high entropy. It's sort of anxious. It looks all over the place before it settles on an answer.
It has a high cognitive load, effectively.
Yeah, exactly. It's considering a lot of possibilities. LaViT, the student, has much, much lower entropy. The coefficient of variation is 0.102 compared to the teacher's 0.392.
It's more confident.
It's more decisive. Because it was only ever trained on a clean, denoised version of the teacher's attention, it learned the signal and completely ignored the noise.
So by filtering the teacher's own uncertainty out of the training data,
you create a student that's more focused than its master. It's not just knowledge distillation, it's like attention refinement.
I want to touch on the efficiency angle here, because a 3B model is a huge deal. For any ML engineers listening, that's kind of the sweet spot for deployment, right?
It's absolutely the sweet spot. You can run a 3B model on a good smartphone, a laptop, on edge devices. If you're getting GPT-4o level visual reasoning locally, that unlocks so much for robotics, for real-time analysis, for things where an API call is just too slow or expensive.
And it's not just good at abstract reasoning, it handles the fine-grained stuff too.
Yes. On the MMVP benchmark, which tests for things where models like CLIP often fail, like counting objects or checking orientation, LaViT 3B showed about a 5% improvement. So it's not just thinking better, it's literally seeing the details more accurately.
So with any paper that claims state-of-the-art results, I always go straight to the ablation studies. What breaks the model? We talked about the gating, but what about the core idea, the trajectory alignment itself?
That was the biggest one. If you take out the liver dollar loss, so you're still teaching the concepts, but you're not explicitly teaching it where to look, performance just collapses.
So that confirms it. The spatial supervision is the main driver.
It's the absolute key.
And they did another really clever experiment at inference time, right? Where they masked the latent tokens.
Yeah, this was to prove the model wasn't just faking it. During inference, they let it generate the latent tokens, Viver dollars, but then they hid those tokens from the text decoder.
Yeah.
And the model couldn't answer the question correctly. It failed.
Which proves those tokens are actually a form of working memory.
Exactly. The model isn't just generating them as some kind of filler to satisfy the loss function during training. It is genuinely loading its visual reasoning into those vectors and then reading from them to construct the final answer.
Something else that stood out to me was their data filtering. They didn't just take the visual COT data set and throw it at the model.
No, and this is a huge takeaway for anyone training these models. They used a 3-stage filter. First, correctness. Obviously, the teacher's answer has to be right.
Standard practice.
Second, difficulty. They threw out any easy samples that a text-only model could solve.
Because if you can answer it with your eyes closed, it's useless for teaching vision.
Precisely. And third, and I think this is the most important, alignment.
What's that?
They rejected any sample where the teacher's own attention didn't fall on the ground truth object.
Wait, really? So even if the teacher got the right answer, if it was looking in the wrong place when it said it, they threw the data out?
Gone. They essentially fired the teacher for hallucinating the process, even if the final result was correct. What they ended up with was a curated data set of high quality looking.
That feels like a paradigm shift.
Yeah.
We've been so focused on clean text and clean labels. This is about clean attention.
It reframes the whole problem. The paper basically argues that a lot of multimodal hallucinations aren't knowledge errors, they're gaze errors. The model knew the answer was in the image, but it just didn't look at the right pixels.
So let's wrap this up. What are the big implications here? We have this white box trajectory distillation showing that smaller, smarter models can really punch above their weight.
I think we're heading for a pivot. We've spent so many years on prompt engineering.
Right. Crafting the perfect text prompt to get the right answer.
This paper suggests that attention engineering, actually optimizing the internal mechanics of how the model looks at data, could give us way better returns than just making models bigger or prompts longer.
And this idea that you can distill and clean up the gaze of a massive model into a tiny one?
It's huge. If a student can become more focused than its teacher by filtering out the noise, could we eventually train a small model to see something that the massive, noisy teacher missed entirely?
That's a provocative thought. Are we getting to a point where how you teach a model to look is more important than what you teach it to say?
It feels like we might be. It's a really compelling future for AI that can actually run on a device in your hand. Refined intelligence, not just bigger intelligence.
If you want to see the heat maps for yourself, and I really recommend it, the comparison between the anxious teacher and the focused student is just striking. You should check out LaViT, aligning latent visual thoughts on Arcuff.
And the code is on GitHub. You can check it out for yourself.
Thanks for tuning in to this deep dive on AI paper podcasts. We'll see you on the next one.